Good morning. My name is Paul Wilson, and I am a hydrogeologist with the British Geological Survey based in Belfast. And I'm the project hydrogeologist for all of the groundwater monitoring boreholes that are being installed in Northern Ireland on the Catchment Care project. And I'm going to be speaking to you today about our practical experiences of constructing and commissioning groundwater monitoring stations on the project. Now, installing a groundwater monitoring station, it's actually very similar to sending a rover to Mars, as many of you have probably been watching over the past few months. And they send a rover to Mars to try and find water, and we drill groundwater monitoring stations to try and find water as well. For a start, they're both not just blindly sent or drilled in any location. Where they land or are drilled is a carefully selected location using all available known information to land a rover or drill a borehole in the place where they're most likely to give the best results for the longest period of time. However, they are still a big shot in the dark and with many unknowns to contend with. But that's why you send the rover or you drill the boreholes, to make the unknown known, to reduce risk and enhance future performance. And without the information they collect, sending humans to Mars or implementing measures to improve river water quality will very likely fail. The one big difference I find is that securing land access permission is a lot harder for groundwater monitoring stations than it is with landing a rover on Mars. I hear that the locals on Mars are a lot more welcoming of the rovers. So in this talk, I hope to impress upon you how valuable properly located and constructed groundwater monitoring stations are to our future. Also, the critical role that conceptual aquifer models play in the siting off and long-term legacy success of a station. And finally, I want to share my big lesson learned so far, being that cultivating solid relationships with landowners is the most important factor in the success of establishing a groundwater monitoring station. So location, location, location. How do you know where to put a groundwater monitoring station? Where do they need to go? This first depends upon what it is trying to achieve. In a catchment, finding out what the quality of groundwater is means it is best to locate a station close to the pour point, so down around here somewhere, rather than up near the top of the catchment where the watershed is. If groundwater is going to be impacted by activity in the catchment, it is more likely to show that down near the pour point. It is ideal, however, to place several stations throughout a catchment in like a surveillance capacity to hopefully pick up something that might be there. Other factors that were used to inform where to locate stations include the availability of space, other partners or projects having established relationships with certain landowners, links with community groups and schools, and accessibility for drilling rigs and plant to be able to get into a certain area. An essential criterion was that a station would have to be available for as long a period as possible, preferably decades, maybe even centuries. These stations are meant to be long-term monitoring stations, which will display their true value only after they've been collecting groundwater level and chemistry data for years and decades. As the climate continues to change, these stations will tell us how groundwater is reacting to it. They will tell us if groundwater bodies are healthy and warn us when they are trending away from a healthy status. And then any potential for future development of a site or a land sell-off was a deal breaker, and such sites were excluded early in the selection process. So we produced a report and a tool detailing the site selection criterion, and this tool was used to score each of the candidate sites to ensure it was valuable enough to have a station constructed on it. So to find sites, first a detailed depth study was performed. This was primarily informed by studies that had been carried out to assess the groundwater monitoring requirements on both sides of the border. These highlighted groundwater bodies that had no groundwater monitoring stations at all, and assessing the status of a groundwater body without any monitoring or data is little more than a guessing game. The depth study used all relevant data sets, such as those shown here, to derive conceptual models for each catchment of interest, and then areas were identified as potential zones of interest. And rather than just cold calling or knocking on doors, we sought to use established connections that the catchment officers or other partners already had. Not everyone is keen on having a borehole drilled nearby, so using established connections, and that helped with communicating what we were trying to do to a receptive audience. Initially, our focus was on publicly owned land to address the legacy challenge, really, mostly. It was deemed safer and less likely that public land would change hands. Therefore, the stations would be available for more monitoring purposes for many years to come. What we didn't anticipate was that securing permissions with different public bodies is very time consuming and in some cases proved impossible. In contrast, our experience with working with private landowners was a real eye opener. I personally found that they were very curious and in almost all cases were keen and willing to help in whatever capacity they could. One farmer, in fact, said to me, if it helps the river and the wildlife, then my land's available to you. They signed a land access agreement there and then. We have still been able to secure some permission on public land, but this has generally taken at least a year and a half compared to normally less than 3 months for private landowners. This highlights for me what is probably my main take-home message of this talk. It's all about open and honest relationships with landowners and communities. If we do something that affects those relationships, then we lose the stations. And being solely focused on the deliverables will cause you to try and convince landowners at all costs to let you drill on their land. There needs to be something in it for them, and to work out what that might be means getting to know them. If the boreholes are not what you promise, your permission will be revoked, and what was the point? If someone's not happy with what you're proposing, let go and move on, was what I learned. Our contractors are briefed and over and over and over again told about the importance of respecting our landowners and their land and keeping them informed during the construction of the boreholes. Things like using special groundwater protection mats and geotextile membranes and designing the drilling area alongside the landowner are just some of the small things you can do to work with them and garner their respect and trust. In fact, I was on the phone with a farmer the other day and we're planning to move on the site shortly to install another groundwater monitoring station, and just finding out whenever they're going to plan to do their first cut and then trying to mobilize maybe after that is just something that they appreciate and respect. I have other views in this, so if anyone's thinking about installing any new groundwater monitoring points in the future, do get in touch and I'd be happy to share more about what we've learned about that. So you have your permission, what next? So we thought that because many of the catchments we'd be working in had low productivity aquifers, that means it's difficult for the water to actually come to a borehole, and there's not a huge amount of groundwater there, that it would be sensible to get some geophysics done to help cite where the boreholes should go to be able to make sure that we actually intersect the various fractures that we needed to drill into and to characterize the ground conditions as well. So far, we've found that it's helped in certain cases, but not so much in others. The availability and the size of the sites often constrain where drilling can take place, and it may be more effective to carry out surface geophysics after drilling sometimes, and to use the results from the drilling to inform modeling of the geophysics data to help characterize the surrounding area. So you've got your drill points marked out. All you need now is a driller. And on this project, Tally from the GSI worked tirelessly to pull together a framework for drilling contractors. The successful contractor carries out its site inspection with a supervising hydrogeologist and comes up with a site plan, a health and safety and environmental management plan prior to mobilizing on site. These are often discussed at length with the landowner and regularly revised to accommodate their requirements. On each borehole that is drilled, there is full-time supervision by a suitably experienced hydrogeologist. This, in our view, is essential to the long-term success and value of the boreholes drilled. So much information can be collected and observed during the drilling about the boreholes and the aquifers they're drilled into. This information can be critical to designing monitoring, pumping tests, understanding the monitoring results that come in later, and for using the boreholes for future research. The design of each borehole is preliminary and only confirmed on site by the supervising hydrogeologist. What is encountered during drilling and the purpose of each borehole go into the final design. In our cases, we're using UPVC casing and cement grout to seal off the horizons that we don't want to be monitoring in a borehole and leaving the bottom section, the response zone, as open hole whenever we're in rock and whenever it's competent enough to stay open. Each groundwater monitoring station consists of between 1 to 3 boreholes, each with a different response zone. So have we found water yet? Yes, we have. We've only started to collect some groundwater chemistry data in the past few months, but already the results are exciting. Each time new data comes in, it's a bit like the folks at NASA as the images come back from their rovers on Mars. We're peering into an aspect of Earth science that no one has ever seen before. These are the locations where boreholes have already been drilled. These are in the Finn and the Derg catchments so far, and total 16 boreholes. And contractors are about to start work in the Blackwater catchment at the start of June, and then over at the Affby Hillsborough farm at the end of July. So by September, we should have at least 34 boreholes constructed, with more to come in the Finn and the Blackwater catchment, which should bring the total close to the magical 50 number that we're aiming for. Once a borehole is completed, we perform a short duration pumping test on it. You can see here in this photo that actually this borehole has literally just been finished, and the next borehole is being drilled, about to be started to be drilled over here. So we're doing a pumping test on this. This helps to design monitoring and future longer duration pumping tests, basically understand how the borehole works and operates a bit better, and allows us to be able to make better decisions. It also helps to help to remove any residual fine sediment from the borehole, which helps a lot when it comes to sampling. We install water level loggers in the boreholes, and the intention is to place permanent sensors that send the data over the mobile phone network so that the data can be viewed in almost real time online. So what have we learned from the 2 catchments we've drilled in so far? Firstly, and again, the relationships with the communities and the landowners are the most important thing to the long-term success of a groundwater monitoring station. Regular communication, discussing the results with them is not wasted time, and more effort should be put into this aspects and towards the end of the project, and if possible, beyond that again. Secondly, our decision to use conceptual models to design the monitoring has been proved correct. What we hope to encounter is by and large what we find. This supports the use of conceptual models in tandem with monitoring stations as a reliable way of protecting groundwater resources, and then also looking after the quality of the water that's in our rivers as well. Once groundwater is polluted, the effects are long lasting and almost permanent, so discovering this early is vital for our groundwaters, but also our rivers that depend upon them. Linked with this, where high resolution geological mapping is available, the accuracy of our conceptual models is greatly enhanced. This data is literally the foundation of our conceptual models. Field geology mappers are therefore very valuable, and improving our geological mapping will improve how we can do catchment science in the future. Another lesson has been that the structure of boreholes is as critical as its location. A borehole is a three-dimensional object. It's in space and it's got depth to it. And just because you have a borehole somewhere doesn't mean it's monitoring the right thing. 2 boreholes located 2 meters apart, but designed to collect groundwater from different horizons can have very different groundwater, very different chemistry, very different groundwater levels. And we'll see a wee bit about that in a wee minute. Also, don't scrimp on airlifting of fractures during the drilling whenever you encounter them. We find that time spent airlifting saves pumps, and it does a brilliant job at cleaning fractures out of silt and sediment that can fill up a borehole later and can cause sampling pumps to need repaired, and also actually skew and affect the results of the samples and the testing that you carry out later. So I hear you crying, show us some data. Okay, here we go. So these are some of the boreholes that have been drilled in the Fen. These are borehole logs or construction logs of what we have. And these are 3 boreholes that were drilled all beside each other. These have mostly been in pre-Cambrian rocks, so schists, sammites, and semi-peelites. These are old, hard rocks that contain only limited amounts of groundwater with lots of minerals, such as iron and manganese. We find that inflows have a high variance. Some are just small trickles, and others are quite sizable inflows, capable of supplying a medium-sized business. In fact, this borehole here, it was drilled to 102 meters in the Derg catchment and encountered numerous hydraulically active fractures that you can see on the side here. And when we pumped it at a rate of around 1.5 liters per second, the water level only came down by just 4 meters. That shows us that it's a very productive borehole, and it's a very surprising result for these types of rocks. Sampling and monitoring data are still limited, but so far it affirms the idea that groundwater is very clean in these catchments. We have no pesticide detections and only small concentrations of nutrients in 2 of the sand and gravel boreholes. This could mean a couple of things. Groundwater may not be a significant pathway for contaminant transport in these catchments, or the groundwater could be diluting contaminant concentrations in rivers, helping make things actually look better than they really are. These are some of the groundwater level measurements collected from the Derg catchment already. And these plots show that these are 2 boreholes located right beside each other, as I was mentioned before. This top one is in a bedrock, so this is the deeper one. And this is the sand or gravel one, so that's the shallower one. You can see how the groundwater levels respond to recharge events and dry periods and how they are different. This is the rainfall here, so you can see what's happening in the catchment and how the water levels respond to that. The higher water levels are in the bedrock boreholes, and this indicates that we have upwelling bedrock groundwater, most likely providing base flow to the Mournbeg and the Derg rivers. Something else that we've spotted is that the bedrock levels have this curious sawtooth pattern throughout. Now, I initially thought that this was maybe from groundwater abstraction nearby from maybe a farm or something like that, and the water gets turned on at the same time every day. But it looks likely that this might actually be evidence of what are known as earth tides, because they have this very regular 24-hour period. We've just discovered this, so hopefully there's going to be more in this later on in the future. The final thing we've observed is that our groundwater levels beside the Derg River are always at a higher elevation than the Derg River stage. So this is the stage down here, and these are our groundwater levels. And these boreholes are literally within 5 meters of the river. Groundwater therefore must be contributing to base flow in the Derg River and is an important inflow to the river, especially during dry periods like what we've had over the past few weeks. This is likely diluting down the concentrations of some contaminants such as MCPA and nitrate. So to conclude, our plans are, once the groundwater monitoring stations have been installed, to have data packs for each one, including all the baseline data collected. These will be publicly available. The plans for the stations are for them to be available for the likes of the NIA and the EPA to use as part of their national groundwater monitoring programs. On top of that, we'll be facilitating ongoing research and education of groundwater resources using the newly established stations. And if we're able to meet together beside a station at some stage before the end of the project, it might be nice to actually have an official opening as such. So again, what's my main take-home message? Relationships, good, mutually respectful and honest relationships with those living in a catchment should form the basis of all work to construct groundwater monitoring stations, but as well any catchment science and improvement works. Thank you very much.